Okay, so now in order to discuss the significance of the gradient vector, we first need to talk about directional derivatives. Okay, directional derivatives is defined as the gradient vector of the function at, let's say, x0, y0, right, has the dot product and the dot product with u, a unit vector. And this unit vector dictates the direction. And the reason that we want it to be a unit vector, this is important because on the test, you may be given a vector u and be asked to find the directional derivative along the direction of u, but u may not be a unit vector. You have to normalize it to unit vector first because we want this, geometrically speaking, we want this directional vector to dictate the rate of change in terms of, like, we want it to dictate the direction for calculating rate of change, but we do not want it to affect the magnitude, right? So we want this to be a magnitude of 1 so that it doesn't affect the magnitude of the ultimate rate of change in the response variable of z here. Okay, so then what this is saying is basically this dot product would just be f of x. I'm just going to write f of x and f of y here. Dot product, let's call this u of I and u of j, the x and essentially the x and y lengths, right, for the unit vector. So then this would just be f of x at x0, y0 times unit of along the x direction plus f of y x0, y0 times the unit vector's y direction. Okay, and then so basically this makes intuitive sense, right, as well. So if I were to draw out x, y, and z coordinates here, and then let's just keep using our wavy surface example here. So this is our plane, this is our x0, y0. So that's our point. That point corresponds to the z0 value on the plane, right? And basically at this point, the significance of f of x and f of y is basically saying if we were to deviate from this point in any direction, very small, by a very small epsilon movement, right? If we were to deviate from this point, z will change according to these partial derivatives, right? X changes by a small unit, then fx is the rate of change in the z value, and y change by a small amount. This is how z would change. So basically, naturally, the unit vector elements along the x and along the y directions, axes, they just tell us, okay, so based on the partial derivatives, we know the partial derivative fx tells us this is how much z changes if x were to change by a small amount, right, by a unit amount. So how much so how much do we want x to change by? We want x to change by this much. So that's going to give us how much z will be impacted by. And then similarly, this is how much we want to move along the y direction, and multiply by f of y. This is how much the z value will change. So together, this will give you the value of change in z with respect to, or in the direction of u. Okay, so that's that concept. Directional derivative is just the gradient, or rather the partial derivatives multiplied by the by the movements along the x and y, along the x here and along the y directions given by this unit vector here. Okay, so now basically directional derivative, we just talked about it in terms of the concept, is just the gradient of x at, let's say, x0, y0 times the u being a unit vector, and this is the dot product. Okay, so now basically now we can see that a dot product identity is basically this gradient vector dot u equals to the magnitude, or rather the magnitude of the gradient vector times the magnitude of the unit vector, which is just 1, so we can just ignore it, times cos theta, meaning cos theta is, so let's say if this is where the direction of the gradient vector, and this is the direction of the unit vector movement, the direction of movement we want to examine, and this is the angle here, theta, then this gradient vector, this directional derivative dot product equals to this, basically just equals to the gradient vector times cos theta. Okay, and then we can see that this is maximized. We can see that this is maximized when cos theta equals to 1, right? Meaning this is maximized when theta equals to 0 degrees, meaning when the direction u is the same as the direction of the gradient vector, that's when we have the maximum change in z, right? And that makes intuitive sense because let's say the gradient vector by definition says if we move at this point x0, y0, if we move in this direction of x and y, if we move in this direction, then that's going to cause an increase in z, right? So if we deviate from that direction, if we were to move in this direction, then we're not, in layman's terms, it's like we're not taking full advantage of the rate of change along the x and y direction, right? It's like we're only it's like we're only taking part of the effect caused by change in x, and we're only taking part of the effect caused by change in y, right? So that is the theorem. So basically what this is saying is the main identity you need to remember is in this direction, in the direction of the gradient, is max change in the response variable, or the z variable. And then just in case, next I'm going to talk about this identity here in the proof here. So basically the dot product equals to the magnitude of the first vector times magnitude of the second vector times cos theta. Okay, I'll talk about this next.